Hello, and welcome to another episode of Yummy Data Science. In this episode, we're going to talk about model validation, and we've been talking about predicting readmissions in hospitals. And this conceptual understanding of model validation is going to be in the context of validating a model that predicts readmissions. So, the key question here is if this concept is unfamiliar to you, or even if it is familiar to you and you don't really understand why we do it, is how good is your model on data that the model has not seen? Any model can be great on data it has seen, but the question here is how good is it on data it hasn't seen yet? So, and the reason we do model validation is that we know that our model is good on the data it has been built with. So, for example, in the readmissions case, we know that, say, these readmissions data came from one hospital. So, we have created that model for that hospital, and the model is great for that hospital. But what if our goal is to generalize the model for like hospitals, maybe nearby hospitals or hospitals with the same specialty? Then what do we do? The generally agreed upon approach here is that of all the data that you have, you set aside some data for model building or model training, and you set aside another set of data for model validation. And you figure out whether your algorithm that you developed in your model training is going to work on the data that the model hasn't seen. And the next concept, terminology may be a little bit difficult, but if you don't understand it, don't worry about it. So it's a classic variance bias dilemma. You increase the variance, you might be decreasing the bias, and vice versa. And let me explain about model variance and bias in our case. So, say you have a model that is very good for your hospital. Well, because it's so good, then the variance, you have managed to explain a lot of the variance in that hospital using that model. But it's not generalizable to other hospitals. So it has a bias towards other. So low variance, high bias, and vice versa. And you want to come up with some ideal mixture of the variance bias um, matrix to figure out what your sweet spot is going to be. So there are three main approaches to model validation. The first is a very standard approach, and I've already talked about it. Well, you set aside some data, a large portion, a lion's portion, 75%, 80%, for model training or model development, and you set aside the remainder for validation or testing. Okay. But some people would argue, well, then we are not using all of our data that we have. We're not using all our information. Well, and here comes the second and the third method. The second method is k-fold variation. It sounds confusing, but it's not. Think of a number for k. Say it's 4. So basically, you divide your data into 4 equal parts, and we'll call them A, B, C, D. And then what you do is you train with A, B, C, and then you validate on D. So now you are taking 75% of your data and validating on 25%. Then you take the next ABD, which is also 75, and you validate on C. And then you collect your validation scores. And I like to call this validation algorithm k-fold validation. And generally, k of 5, 6, 4, up to 10 works well. But it's really an art you want to try out. I like to call this approach have your cake and eat it too, because you are using all your data for training, but you're also using all your data for testing. So it's kind of nice. Um, and if your data is big enough, then you can say, okay, 75 is pretty good. I'm going to divide it into these folds of 75 and then validate on the remaining 25%. Now, an extreme case of k-fold validation is when k is equal to the number of observations in your data set. So k is not 4, k is not 10, k is equal to, if you have 500 observations in your data set, k is equal to 500. What does this mean? This means that you train with your all but 500 observations and validate on one observation, your 500th observation, and you continue like this. Now you have created 500 different types of models, and you have 99% of the data for training. Actually, it's way more than that. And you are scoring it on one observation, and then you're adding up how you did. So this is the ultimate case of have your cake and eat it too. Now, some of you have already figured out that this approach is computationally intensive. So whenever possible, try out all three and at least one or two. So we've talked about validation, and we've also talked about what you can sum up across validations. Well, what is when you validate your model on, say, 10 observations, what does it really create? Well, it really creates a matrix, a confusion matrix. And this is interesting because confusion is, a lot of people are confused by this. And it's tricky because it's all these true, false, and etc. But it's actually, if you think about it in a simplistic manner, it's not that hard. On the y-axis, we have actual. So this is what the classes were. Were they readmits or not? Were they positives or not? And then here are the predicted. What did the model predict it was? Positive or negative? And so now you can see that the green quadrants are when the model got it right. So these are of the positives, which are these guys. The model got this one right. Of the negatives, which is this two quadrants here, model got these right. Now, when you validate a model, the model doesn't give you these classes. It gives you probabilities. So what a human needs to do, what a data scientist needs to do, is come up with a threshold. So you could say if the probability, predicted probability is greater than 0.5, then I'm going to say this is a positive. Or you could say if it's greater than 0.65, then I'm going to think of this as a positive. So you need these threshold values, and you can play with these threshold values to to place more emphasis on either the true positives or the true negatives, whichever is your focus. Another thing that confuses people is the statistics, sensitivity and specificity. And to be honest, if I haven't worked with this for a while, I have to jog my memory. And I've been working in this area for 30 years. So sensitivity is this. Of the positives, how many did the model get right? So recall, these are the positives. These are the actual positives. So we have true positives plus false negatives. These are the actual. And then sensitivity is how good was the model at figuring out which are the positives from all the positives. Okay, so we obviously want the model to be sensitive. We also want the model to be specific. We don't want it to say that it's a positive when it's not a positive, right? So this is being specific. And here, this is this. These are actual negatives. And of these, how many did the model agree that these were negatives of the total number of negatives, which is the second two quadrants right here. So the moral of the story is validate early and validate often. Whenever possible, do all three approaches. And now in the next episode, I will show you these with respect to logistic regression in Google Colab. Thank